Okay, welcome guys. So this is a part of the category lecture. So today let's talk about the functors and the natural transformation. Okay, so still many definition. So let's define a covariant functor. Okay, so very simple. So functor basically is from category to another category, D. So C from D. And then we know that there's object, right? So the definition of the functor means that for each, let's say you're given a pair from A to B, which A, B are but just the object of in C, and then there's a morphism. So you need to map into object in D and object in B, and there is a map, right? Basically, it's F, small f. Right, so given A, B, and small f, you need to give me FA, FB, and FF. Right, so this is the first data. Okay, and the second data is that you need to make sure that the identity homomorphism A from A must be mapped to FA. Okay, and the third is that the composition work. Okay, this is called a functor. Okay, right. So trivial example is that you change. So for identity functor, basically map every identity, every C to C, so every object to itself, and then morphism to itself. Yeah, so simple results. Okay, so if we have a functor, then we can definitely give the isomorphism of categories. Okay, so the definition means that if two C and D are isomorphic, means that it is the functor C to D and another functor D to C, such that F composition G will be identity and G composition F will be identity on both D and C. Okay, so simple definition. Okay, so some words. So we say functor is injective. Means that as a function. So basically, f is injective. So if you just if you view basically for each one, if two different objects in C must map to into these objects, and the same is surjective, and many other words. Okay, so yeah, so it should be intuitive. Okay, so let's give some common functor. So given any functor C map to set, it's called the faithful functor. Let's see. Oh, so let's maybe see maybe say this. So let me introduce a functor called the forgetful functor. Okay, so this functor is a interesting one. So basically, for example, if you maps the group's functor to set a group's category to set category, so basically someone to give a group G, and you forget about you just forget about the structure of G, right? So map into the set. So which is the same as G, but you forget the group structure. And easy to see that this is the functor, right? So basically, if you can also map rings to sets, also topologicals to sets. Okay, so this is called a forgettable functor, which is common use. Okay. Okay, so let's maybe talk examples which are more useful. So basically, this is copied from the standard algebraic topology, right? So algebraic topology tell you that if you have a topological space, right? Give a topological space, then you can associate it with each integer, positive or greater or equal to integer to homology group. So basically, for each topological space, you can compute a homology group. Okay, so this is maps to abelian groups, right? So for each x, then there's a abelian group, right? So this is a functor. Okay, and it's a covariant functor. Okay, so there's another definition called the contravariant functor. So contravariant functor means that the same reason, the same construction base, but for each a, b, and f, you need to construct you need to map into the reverse. So start from fb and fa, but the arrow is reversed, right? So basically, you need to construct another morphism from b to a. So fa is still the same, fb is still the same, but the arrow is reversed. Okay, and also identity must be identity, and also composition. I need to change directions. Okay, so example is called the very famous example is the cohomology. Okay, so this is a very large class of the covariant functor because there is a various cohomology, like singular cohomology, or basically the round cohomology, or Itaco, or basically there's a lot of different cohomology. Okay, and finally, let me just mention small results. Let's collema. So this says that right, if you have any contravariant functor from C to D, and then you can easily change the direction, right? So it tells you that any contravariant functor must corresponding to a covariant functor. If you just do the opposite category, right? Because opposite category means that each arrows reverse, right? I map to D. Okay, and call it F prime. Okay, and also you can another is that you flip the D, right? So any contravariant functor will corresponding to different covariant functor. Okay, so the proof is basically trivial. Okay, so up to now we only talk about some trivial things, right? We always talk about definition. Okay, so let's talk about a natural transformation. Okay, so people usually think categories are boring, right? Actually, but it's interesting if you have some concrete examples that you have learned. Otherwise, that the learning category theory is truly boring. Okay, so natural transformation should be viewed as the morphism between functor. So I should say between functors. So let's say you have C to D, right? Two functors, let's say F and G, right? So okay, so maybe I use a small g. So that means that if somebody give you A and B, then you then a morphism F, then you will have this. And so if you give you you also have G and GA and GB, right? Okay, so so what the natural transformation, right? So the natural transformation, it's called data, right? So natural transformation is a data that from each A. So if you give you FA and I need to map to F, I need to map to let's see. So if somebody give you any object FA, you need to map to GA. So where A is an object of the category C. Okay, so it's a little bit trouble. So let's clear. Let's make clear. G map, right? So basically, and A is belongs to the object C. So basically, for each two objects, right? If you map into D, then I need to for each D, I need to give you the corresponding map, right? So These are basically theta A and theta B. Okay. And then make this diagram commute. If such theta exists, then we say that this is the natural transformation from two functors. Okay, and also let's also define another called the Functor category. Okay, so Functor category is not, it's just let's, so for any two categories, you can define a category of functors from C to D. Basically, object basically right, trivial from obvious trivial right functor from C to D, and the morphism are just what natural transformation. Okay, so that's finally given definition called the equivalence of categories. Right, so if you have a category, you have categories C and D. Equivalence means that you can find at least a pair of functors from C to D. One is called epsilon, one is D to C. And also a natural transformation. There's a natural transformation called alpha. Right? So this general transformation will map to the ideal functor, identity functor, same as F circle E, right? And so basically it's a generalization of isomorphism of categories. So this is very, very powerful, very, very strong condition that if you say two functors are two categories are equivalent, because it's not dependent on functor, it depends on the natural transformation. Okay, and you have a beta from 1D should be EF, right? So these are natural transformation. So basically you need to construct two functors and also the two natural isomorphism. Okay, so this isomorphism is a view as a natural transformation view. These connect these two, right? So not very difficult. Not very easy. Oh, by the way, I never said so. Morphism is natural transformation, and from this point of view, you can define the natural isomorphism. Because you have a category, right? You can define natural isomorphism. So this means the natural isomorphism in a sense that in this functor category C and C to D sense. Okay, so if they are the same, then we call that equivalence of categories. Okay, so one example is that if you have a set, which is finite set, its isomorphism to order is a equivalent in the category of the partial order set. Okay, that's it. Okay, so that's it. I think it's enough. Yeah, so in this video, we talk about the natural transformation and the functors. Okay, and the next we talk about the limit, co-limit, and the final we talk about the product and co-product.